Our speaker today is awesome. How awesome is he? He's so awesome that if you were a car, he'd be a helicopter. He's so awesome that if you were a plane, he'd be a rocket ship. He's so awesome that if you were a software engineer,
Thank you very much.
If you were a software engineer, he'd be the chief JVM architect at Azul Systems. Ladies and gentlemen, Cliff Click.
Thank you. Well, that was a little more of an intro than I usually get. I at least have somebody fooled. All right, so this is me rambling about what goes on inside of a JVM, having worked on them for almost 15 years. It's been a long time, and I'm still amazed at what goes on inside of a JVM. And there's a huge pile of services, and people have been adding services to JVM. The last time, I'm sure everyone's right here, many of these services are sort of volunteered to the JVM engineering teams by naive changes in specs, which turn into like horrible, long disasters of engineering efforts to make them do something useful. So some of the services involve high-quality GC, and this is like one that's on everyone's mind because there's so much engineering effort to put in to try and get GC pauses to be reasonable on these ever larger and larger heaps. But really, the GC that's in there now is pretty amazing compared to what was available 10 and 20 years ago. The actual total allocation costs are quite reasonable compared to the alternatives, and the GCs are parallel and concurrent and incremental and yada, yada, yada. They have all kinds of cool features about them. There's a high-quality machine code generation going on in there. Hotspot has 2 different JITs. Most of the VMs out there have several different JITs in motion at once. There's management of the JITted code. There's profiling. And the combination of these things turns into, it gives you a bytecode cost model. And that's sort of a key bit of transparency that's not one that people often think about. A bytecode cost model tells you something like a get field instruction is typically the cost of an x86 load. Right? And that actually only works because the JIT puts its head around what it means to do a get field, removes all the weird corner cases, optimizes away the null checks and the range checks and everything else on the planet. And in the end, the bytecodes that you get actually have a cost model that's somewhat related to the underlying hardware processor cost model. And then there's uniform threading and memory model, and this is basically tells you the meaning of multi-threaded programs, what it means to have 2 threads where they read and write the same shared memory, and whether that's correct or not, or how the data flows and when and how and why. It also gives you type safety, and that's crucial for large programs. Your C programs do not get that and suffer from weird bugs the same, that kind of a way. You get to do things like load code, and when I say load code, I don't mean just loading new code and running it, but loading it and running it using all the same services that are already there, meaning it has the same bytecode cost model, despite the fact the code was not available when the JVM started. You have a long-running server, you download them code over the web, it's just as fast as if you had it locally on the spot, and that's because you optimize and re-JIT on the fly. High-quality time access, I'll talk about that because it led to one of the more horrible things inside of a JVMs. There's a lot of introspection services, JVM TI, DI, PI, agents, reflection, yada, yada. Huge access to a huge library, access to stuff in the OS, threads, scheduling, priorities, things like that. Those are all brought through the JVM and available to your Java program. So where did all this come from? So most of these services were incrementally added over time. The hotspot, 1.0 or Java Virtual Machines 1.0 didn't have all this stuff. But the language, the JVM, and the underlying hardware have all co-evolved over the last decade. Right? So the incremental addition of like finalizers were the thing that weren't there originally and were added by people who wanted it. Same with the Java memory model when we started seeing lots and lots of multi-core systems and we had to know what it meant to have 2 different threads on this running concurrently to communicate. 64 bits was added when it became clear that we were going to have lots of machines with 64-bit capabilities. Support for high core count, and that means different underlying algorithms in use in the JVM itself for concurrency, for scalable concurrency. If you want to run a garbage collection on a 100 gigabyte heap, you're not going to run it on a single thread. It's going to take too long. So now you need a garbage collection that scales well to all the cores that you have available, right? And now the real question is why? The services came, but why did they come? They came because the services provide an illusion, a powerful abstraction. It changes, it puts a dividing line between where the JVM engineers innovate and where the writers of Java code innovate, right? So people who are writing Java focus on adding value above the JVM layer, and people who are implementing JVMs provide services below the JVM layer. And that separation is similar to the separation between x86 and the programmers who write software on an x86. It's a great place to draw the dividing line between who's doing which piece of work, right? Now, if I look at these set of services, though, I see that they've been very ad hoc. They've been grown over time as people have requested or needed. Some of the services are unique to Java or unique to the Java virtual machine, but a lot of the services sort of overlap with prior existing services, but there was some stupid requirement that wasn't quite right, and so the actual service, like priorities within Java and priorities as they exist in the OS are not quite the same thing, and they don't do the same thing, and they have slightly different jobs, and you can't end up using the same priority mechanisms. And I'll have some more discussion on that, but there's a lot of these services that fall into that camp. They look like they're similar to what's been done before. There's some stupid thing that's different, and we had to, replicate that service the hard way. Okay, so that was my intro. Let's talk a bit about the illusions that we have, the abstractions that we have. And the big one is obviously garbage collection.
It's just a call and it'll fix it.
It's the illusion of an infinite heap, right? Just allocate memory via new, and poof, you got some memory, right? Don't bother to figure out when you're done with it, track its lifetime, whatever. GC will figure out what's alive and what's dead and do the right thing, recycle the dead memory. It's just so much easier to program than malloc and free that it lets you write code in an entirely different way. You can remove a huge class of bugs from your mental thinking process, and that means you can write code quicker to get the same job done. Quicker time to market, usually. But on the other hand, you might take quicker time to market to turn into more time to add more features, or more time to add more performance work, or more time to do whatever. It was just a lot easier to use GC than without it. And then it turns out that it enables certain kinds of concurrent algorithms that you simply can't do without it. It's just too hard to track liveness on a bunch of these interesting concurrent algorithms. And in particular, the JDK5 locks, the Java util concurrent locking mechanisms, do allocation in a way that requires a lifetime management that's not really feasible without using GC. They're fundamentally, those locks require GC to function. Okay. More on GC. There's these huge strides we made in the last decade. We went from having a GC that was good enough to use in production in a lot of scenarios, fairly reliable, but didn't scale real hugely well, and still had all kind of weird corner cases, and still had issues with very large heaps or with pause times, whatever. And people have been adding more and more and more features to the GCs over time. So it's robust, it's parallel, concurrent, but there's still too many GC tuning flags. At least I claim there are. This is a major point of differentiation among different people who are working with different GC algorithms. It's a source of active development. Throughput on the different GC algorithms might vary by as much as 30%, where the very concurrent, very low pause time GCs have higher overheads than the sort of stop the world ones. So here's 6 orders of magnitude on pause times. Azul will sell you a machine that'll take hundreds of gigabytes a heap with a 10 millisecond max pause. IBM will sell you a machine that has hundreds of megabytes, not gigabytes of heap, but with 10 microsecond pauses. This is good enough to do hard real-time stuff, and I in fact know that they are doing hard real-time stuff like avionics control systems and the like. And the stock GC starts having serious pause issues when you head for the tens of gigs of GC of heap. And then CMS and G1 fit in there, and there's other GC algorithms floating around. So there's that illusion. So let's move on here. So bytecodes are fast. It's a nice illusion. Bytecodes, in fact, suck as a way to describe programs. They're rather horrible, but we're sort of stuck with them now. The main win of bytecodes, though, is it does hide the CPU details. It's a way to describe a program without knowing what the actual underlying hardware is. 10 years ago, this was interesting as a differentiation between x86 and Spark, or x86 and Power, or x86 versus something else. These days, it's the low power side. It's x86 versus ARM chips, or MIPS, or whatever goes in a iPad, iPhone, yada yada thing, right? So really what we're doing with the bytecodes is that we're expecting them to be fast, but if I do sort of the naive interpretation of the full semantics of a get field or get static, they're actually pretty slow because there's a lot of work that goes on there. And JIT'ing brings back the expected cost model. It lets me have bytecodes and kind of believe, oh, that'll turn into something that's reasonably efficient. And it actually only works because the JIT does all kinds of magic tricks. So eventually the bytecodes have to be JITted. Right, and the JITs themselves are these days are very high quality optimizing compilers in their own right. They're giant, complex things. 20 years ago, an optimizing compiler that's now inside of Hotspot would be considered one of the most complicated programs on the planet. These days, it's just part of JVM, right? And the other kind of thing that's interesting here from a historical perspective is it brings sort of GCC-02 that level of optimization to the masses. Every time you guys run hotspot-server, you're running an optimizing compiler under the hood. So it probably is the most executed optimizing compiler on the planet now, or at least it's going to be really close to GCC. But I can't just pick up GCC directly. Why don't I just why write your own optimizing compiler? Well, this is one of these services that didn't work to use the existing services that are out there. There's lots of compilers. 20 years ago, 10 years ago, lots of optimizing compilers out there. Why wouldn't any of them work? Because they don't track pointers for garbage collection right. They didn't do the right thing there. They didn't do the right thing for the Java memory model, which has strong requirements on how you do reordering of loads and stores and fences. And I'll talk more about that in a minute. And then there's just some new code patterns that needed optimizing. Things that weren't happening in C and Fortran programs were happening in Java programs, needed optimizations, things like class hierarchy analysis or null pointer check eliminations. JIT'ing requires profiling, at least a minimal amount of profiling, because you don't want to JIT everything, right? And profiling allows you to focus your code generation efforts on the small pieces of hot code, which happen to be the case of all modern programs, right? But profiling allows you to do better code generation than sort of static compilation, because you know something about the code you're looking at. You know what methods are hot, so you know what to inline, where to do your heavyweight optimizations, throw the work. The big effort from the compiler gets put down in the right places. And then just, general profiling turns out to let you do better things with code layout for branch prediction or spill code generation or instruction scheduling, things like that. There's a bunch of stuff here. And basically, everyone gets to use profiled code. If I look at sort of static optimizing compilers for the old spec-int, spec-fb style stuff, profiling those machines, those programs was worth 15% or more of sort of raw speed up over non-profiled but fully optimized code. So profiling has a real interesting, real benefit to the performance of your code. Another illusion we have is that virtual calls are fast. C++ has virtual calls, kind of introduced the notion of it, but they avoid it by default because you have to ask for it, and they avoid it because it's slow, requires multiple levels of indirection, including, in the end, a jump indirection off some table. Java sort of embraces them. So by default, everything's virtual in Java unless you say otherwise, since you add the final keyword to say the negate. It's not virtual, right? Well, that makes them common, and if make them common, you have to make them fast or they're unusable. So mostly, they do get fast. The big ticket item here is class hierarchy analysis, which tells you that, in fact, while multiple targets might be possible in practice right now, there's only one. And if I know what the one is, I can make it a static call. I don't have to do a virtual call. And since it's a static call, I can inline it and do all the optimizations I want to do. But that might change over time. So if new classes get loaded, I might have to rerun my CHA and maybe re-JIT my code. And and that all works. That all is in there and does the right thing. And then finally, if you can't use CHA, it turns out in practice, most call sites that are labeled as being virtual by the programmer are in fact static in a dynamic sense. Only one class of object ever hits that call site for the this pointer. That's the same class every time. You use a simple inline class. It's a classic key-value pair inline in the code. You test the key against the class. If it's the expected class, you've already done the lookup for the targeted method, and you encode it as a call instruction at like the hardware x86 machine code level. And that makes a virtual call that hits in an inline cache basically one clock cycle longer than a static call. It's extremely cheap. But when that fails, you go back to being slow. Turns out in practice, this is almost never an issue. That the number of times you have to do the load, jump register to get the virtual call table lookup is so vanishingly small that it makes no difference on any real program. Partial programs are fast, right? This is the whole, I didn't have the whole program at startup time. This is the open world model instead of the closed world model, right? You can say class for name and get new code loaded in. And then that runs as fast as code that was there all along because you optimize it and you may have to de-optimize old code and reprofile and re-JIT to get there, but that all is in there and that all works. You can add code on the fly and it's just as fast as if it had been there from the start. A consistent memory model. So this is an interesting one of these days, although 10 years ago it was highly unknown to people or not thought about, wasn't important in people's minds. All machines out there have different memory models. And the rules vary on visibility vary widely from machine to machine, even within generations of the same kind of machine. So you might think an x86, which has a very conservative memory model, has the same sort of memory model from x86 within across generations. Turns out within a same generation there are some variations. Turns out it varies across motherboards as to the timing of when loads and stores cross back and forth. So the rules here are, in fact, quite variant. It's hard to say what they really are. Power and MIPS have a more aggressive memory model, and Azul and Titanium actually have a very aggressive, allowed wide out of orderings in the hardware level. Now, we map this very out of order, widely varying loads and store timing issues back to the Java memory model by doing something. Okay, let's be next slide. Okay, so really we have to match the Java memory model, despite the fact that we have all these very different memory models from the underlying hardware. If you just execute loads and stores without thinking about the order in which they happen, you'll get programs whose very meaning depends on the hardware you run on. If I ran it on this x86 today and that MIPS chip, tomorrow, the meaning of the program would be different because the underlying memory model is different. So given different memory models, and actually none of them match the Java memory model, they all have to be, the gap has to be bridged by the JVM. But it has to keep that gap bridged while keeping the bytecode cost model. Normal loads and stores have to remain fast. And we do it by some combination of code scheduling, fences, very careful placement of your locks and your compare and swap operators. Requires close cooperation from the JIT. Requires a JIT engineer to have detailed hardware knowledge to do the right thing, to know when he can insert an x86 M fence or S fence or a locked add to the top of the stack, or whatever the hell it is today or tomorrow or the next day on the right way to do this on x86 or Spark or ARM or whatever. Okay, another one, consistent threading models. There's lots of very different OSs that Hotspot or JVMs in general run on. Linux, Solaris, and AX sort of fall in the camp of like pthreads works, and you kind of port pthreads and it's all good. But also you run on other things, cell phones and iPads, or maybe on some 1,000 CPU, mega server somewhere. And these guys have very different OSs, but Java just makes new thread, do the right thing, and immediately synchronized, wait, notify, join, all just work. Your multi-threaded program does the right thing across all these different platforms, and that requires a lot of work under the hood. Okay, here's an illusion. Locks are fast. Okay, so obviously not all locks are fast. If you have a contended lock, and obviously somebody has to block, go to sleep in the OS. So that's fine. But then we might expect fairness from the OS. So if I have 1,000 runnable threads all trying to take the same lock, I might hope for, well, if I'm running it on a 4 and 8-way machine, most of my threads are asleep. They're getting woken up taking turns. I'd like to expect fairness from the OS, and in fact, that's not the case. Most OSs, I might hesitate to say, like all the ones I know about, do not hand you fair locks. So you get thread starvation. It's very easily testable on write a Java program, launch a bunch of runnables, and you can watch thread starvation, especially if you have one thread whose job it is to shut all the other ones down. After he goes to sleep, he'll never get another cycle, and he won't, therefore, shut the program down. So we fake fair locks in the JVM itself. And that requires a huge amount of engineering work to get the right kind of things going on with fair locks. Now, if you move away from contented locks and go to the uncontented locks, they're very cheap these days. And in fact, they're getting cheaper. If bias locking gets turned on, we can expect uncontented locks to be in the handful of clock cycle range. So this is sort of amazingly fast compared to Hotspot 1.0 of 10 years ago, where locks were to be avoided at all costs because they're so expensive. These days, if they're not contended, they're pretty damn cheap. And why did they get optimized? Here's the different question. Instead of they are optimized, why? Because they're so common. People don't know how to write programs, how to write concurrent programs, just in general. So the industry as a whole settled in on this just add locks until it works kind of mentality. So the least common denominator. I don't know why it's busted. I got some weird data race. I'm going to throw another lock in. Throw another lock in. Oh, the bugs went away. Okay, I'm done. Right? So locks become common. Uncontended locks become common because they are defensively programmed in. Right? And so the JVMs optimize them. And we get this interesting concurrent programming style of add a bazillion locks until it works. And as an industry, we have learned a lot about concurrent programming, but what I claim we have learned is that this sucks as a programming style, and we're looking for a better model, and we don't know what it is yet. But it's the model we have right now. Okay, change topics. Quick time access. System.currentime millis. The reason it's in those slides is because it turned into one of those grossest hacks floating around inside of Hotspot. And in general, and I've come to discover today that Google has replicated the hack over again. So under some particular interesting benchmark, not to mention JVB or anything, a winning score will be called, it'll be called billions of times a second. So that's not millions, it's billions of times a second. But it is actually fairly common in all large Java apps. People timestamp a lot of things a lot of the time. they like to throw their timestamps out, and they do that by calling current time millis. But, and here's this little eye chart here, what this little piece of stupid math says is, if one thread thinks his current time millis is less than another thread by even 1 millisecond, which if they're just comparing millisecond counts, they might actually differ by no more than a nanosecond time, but they just happen to be at the edge case where the milliseconds flip, then this thread thinks all his reads and writes are completely available to that thread. Okay, so what that really means is if one guy goes and populates some data structure and reads the current time millis and writes it to memory, and a second guy reads it up and says, oh, it's off by 1 millisecond, even though there might be 1 nanosecond in time difference, the millisecond count value is 1 off, that he believes that all the writes that this guy did are visible in that guy, and he immediately can rely on them being there, when in fact they haven't had time to cross the chip in the caches yet. The light only goes so fast, and so he pulls up a bunch of uninitialized data. And real large, 3-letter company acronym Java app servers will crash if you don't provide this guarantee.
Is that in the spec, or is that something that you just have to do?
It's just something you have to do. It is definitely not in the spec. Okay, so then, this situation kind of stinks, and Intel said, oh, we can fix it. We'll add this TSC register, this nice thing that will count ticks on a running core, and it'll give you can convert it into time. And the obvious way you would convert it to time is just load the thing, add some base, and scale it, and poof, it's going to give you milliseconds, right? But it turns out the value is not coherent across all CPUs. Now, new on Halem, it's coherent within a socket, but across sockets, it's still not coherent. So it varies, it goes faster and slower in some CPUs. So you get 2 different CPUs that's doing this, right? It's all over the map. And that means that if you just read the TSC shift scale add, you get issues where this doesn't work. So it's not sufficient for running large Java programs that way. Right now, a hotspot does current time millis by doing basically an inline version of the fastest flavor of Linux time of day call, which is mostly some sort of user mode atomic struct read. You read some big user mode struct that the kernel's fixing behind your back in a read-only page for the user side, and the user reads it once, and they read it a second time to confirm it hasn't changed between reads. And if they get an atomic read of all the fields, then they use that to shift scale add and come up with current time millis. It gives you a nice quality time, and involves a number of memory fences and reads of memory that are long enough that loads and stores from different CPUs settle out, and so you get the atomicity guarantee that you need across machines. If I read current time millis on one thread and read it on another, they will agree, if they differ by a millisecond, they will agree that all the loads and stores from one are visible on the other. Okay. But a better way to do this, or faster way anyhow, is to do some sort of plain load instruction where the kernel updates the current time millis on some user mode page. That's just actually the milliseconds. I just have to read it. And that means 1,000 times a second I want to tick that one word up in the kernel. Well, that's pretty damn cheap, actually. That's worth 10% on JVB. And if you turn on -XX plus aggressive optimizations on hotspot, it does this. But then that crashes all those app servers. But it's 10% on JVB. So it's a pretty gross situation. And then hypervisors came along and said, "Oh, we can fix TSC. We'll make it idealized. We'll make it monotonically, uniformly ticking across the CPUs by intercepting the reads of the TSC register and doing the right thing under the hood in the hypervisor and handing you back the right answer. But that means access to the TSC register is like 100x slower. It's just as fast as doing this." So it's like, no, that didn't actually fix the problem. It's not this fast. It's that fast. But it's secretly that fast because it looks like it's just reads some hardware register, but it's not. Okay. Moving on. So here's some illusions we think we have, but don't actually, or would like to have. So we'll start out with some like to haves here. Infinite stack. Everyone who likes these functional languages like Clojure or whatever would love to have tail calls, tail call optimizations. And that gives you the illusion of an infinite stack. Running code as data, that's Clojures. That's coming actually in Project Lambda or Coin or some combination of the two. It's going to hand you Clojures, which is essentially code as data. Capital I integer is as cheap as lowercase integer. And that's useful for, again, some of these functional languages which like you to take primitive ints and let you throw virtual calls on them to do, I don't know what, I don't know why, but that turns into autoboxing. Java C, if you use a capital I integer to get started somewhere, and then you do lowercase int-like things like for I equals 0, I less than n, I plus plus, well, the I plus plus turns it into autoboxing. That is, it becomes a capital I integer, and then you have to allocate an object for the capital I integer, and you have to get the value out of it and add one and make a new capital I integer and yada yada. It's like 10 times slower if you head down this path. And it's hidden from you that it happens that way because Java C does it makes the capital integers automatic, and now people like the JIT to undo that under the hood. So that's some piece of work has been done by Sun before Oracle took them over. I don't think it's turned on yet, and I know that it doesn't work very well when it is turned on because I've looked at it. Big integers as cheap as little int. That's silent overflow to infinite precision integers. To do that efficiently, you want to do something called tagged integer math, which requires close cooperation from the JITs and the underlying runtime system. But I think the number of consumers of this are very small. Although some of the new languages want to go down that route, they're going to make all the users of that language pay some hefty penalty, where I think the number of people that need infinite precision math are very small, and they know who they are. So they can just go ask for it. So I think this is barking up the wrong tree, but I'm not a language designer, so I'll quit now.
And it's also evil because it gives you a new kind of memory.
Yes, it does. Very interesting. Okay, other illusions we'd like to have. Atomic multi-address update, which is another funny name for software transactional memory. A bunch of people are playing games here. The JVM and the JIT could conspire to do interesting things there. If this becomes the current programming style of choice, I don't believe it will because it has some fundamental flaws. But I don't know. If it turns out that people like software transactional memory above all other options, then there's things that JIT could do here, JVM could do. And then fast alternate call bindings, this is invoke dynamic. This is like, JRuby has different call semantics than Java does, and invoke virtual doesn't do the right thing. So you want to do some sort of different thing there, but you still want to have to be as efficient as an invoke virtual, which in the end turns into like an inline cache kind of thing. And that's what invoke dynamic's about. So it's not here yet, but it's probably coming. So here's some illusions we think we have, right? Here's the big one. Massive code is maintainable. Hotspots approaching 15 years old, and large chunks of the code are very fragile, or honestly very fluffy per line of code. There's a lot of code per unit of work done, right? And so you get a very slow new feature rate of change. Things don't get added to hotspot very often. Like in invoke dynamics, the biggest, newest thing to get added in a long, 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 long time. We've been busy rewriting lots of it. That was the fun part of going away from a big corporation to a startup. And I, in fact, have rewritten lots of subsystems to become, faster, simpler, lighter. And it's just sort of a the takeaway from this is it is possible to fix hotspot to give it new paint jobs and get rid of a lot of the really crufty stuff. It just hasn't been happening at Sun. Or who knows what Oracle will do now. Okay, more illusions we think we have. Thread priorities. People think we have thread priorities because obviously the OSs have thread priorities and they work, right? Well, it turns out they don't. Linux has, for instance, thread priorities, but you can't raise your priority without being root, and everyone starts at the default of max, which means that you can't lift your priority without being root. Well, that means if you want to have a concurrent GC, which wants to provide sort of hard real-time guarantees on your GC performance, that needs cycles. And if you have a lot of running mutator threads, they're competing with those GC threads because everyone's at the same priority. Unless you lift the priority of the GC threads above the mutator threads, but that means you have to run as root, and that's an ops guy's nightmare. Every JVM runs as root in order to get priorities for, okay, so bad news. You get priority inversion, you get a bunch of issues. Another one here is, next slide I'll talk about this one. You get priorities that are relative to the entire machine, but you need priorities that are relative within a JVM as well as across machine. It's a different notion of priority. And then obviously, we think we might have write once, run anywhere, but scale matters. Stuff you do for small scale, low power, low battery machines is very different from what you might expect if you're running on a quad socket 8-core Nehalem thing. You need, one matters for memory size, footprint, and power consumption, and one says I got to have tons and tons of threads. Got a lot of giant heap. I got to have giant I/O things. I have different programming styles. Okay, finalizers. People think finalizers are useful. Somebody does, because I see them all the time, but they're not. But they think, but you're led to thinking that they are. And what the issue is, of course, is that it's a way to reclaim OS resources, but there's no timeliness guarantees given. The code will eventually run, but eventually could be, heat death of the universe kind of thing, right? And the obvious example here is something like Tomcat, which churns through file handles as part of accessing web requests. And you can trigger an out-of-file handle situation, which requires a full GC cycle to run the finalizers to reclaim the OSs, the OS resources of the file handles. And in the olden days, when heaps were small, you ran full GC cycles fairly often, and your file handles got returned in a timely fashion. And the newer machines with more memory, you return through file handles faster than you run GC cycles, and so you run out of file handles. And so there is a backdoor hook in the out-of-OS file handle resource thing to tell the GC to go run an emergency GC cycle, reclaiming finalizers as best you can, in the hopes that this, and then you can go re-ask the OS, can you give me a file handle now? And maybe he can, right? But do we really want to program our systems this way? Every time you add a new OS resource, you have to add a backdoor to the GC to say, go run a finalizer now, and just in case something comes back out of it. It's sort of the wrong way to manage resources. Soft phantom refs, weak refs, maybe weak refs are useful. And this is basically another case of using GC to manage a user level resource. In this case, usually user mode caches. And the idea, of course, is you have a cache that holds on a lot of stuff that you might need, but sort of optimistically in the cache. And then if you're low on memory, can you throw stuff out of the cache and then reclaim a bunch of memory, right? And so what happens, and I've seen this happen on a number of occasions, you get some sort of low memory situation which is going to run a GC cycle. Well, the GC cycle flushes your soft refs. The GC has no clue what a soft ref points to at the user land. It's just an opaque soft ref thing. So he has to choose some. He picks some random set of soft refs to clear out, and that causes your cache to flush. Well, then you're going to miss in your cache because the user app was using the stuff in the cache. It was doing what a cache does and saving you from work. So you have to do all the work that you would have saved had you hit in the cache. And all that work causes you to do some more allocation. And since you're low on memory, you do another GC cycle, which flushes your cache again. And so what happens is you have some sort of server which is behaving nicely, and as you add load, the load ramps up. The server's throughput matches and ramps up with it until you hit some threshold of out of memory, getting close to memory edge. And then, of course, the load never comes to in some uniform, easily scaling thing. The load's bobbling up and down as it ramps up, and you get a little bobble at the wrong time of a GC cycle, and suddenly you have low memory situation, and you're trying to hit in your cache at the same time, but your cache flushes, and you hit this cycle where your cache flushes, you do a bunch of work, now you have to GC again, and you get in this endless GC cycle where the server's doing GCs constantly, and every time he does a GC, all the load has to do all the work the hard way because the cache isn't functioning anymore. It's been stripped clean, and since it does all the work the hard way, his throughput sucks, and he fills his memory up with all the work to refill the cache, but then the cache gets wiped clean again. And the throughput on the server crashes and remains low until you take the load off, long enough for GC to catch up, quit flushing the cache, and let you start applying load again gradually. And of course, at this point, people just think the server has crashed and they reboot it, which is sort of another way to get the same thing done. So I claim that the failure mode in this scenario is you're asking GC to make a decision about your application level performance, application level's behavior, without that GC having a slightest clue what the application level behavior is. He doesn't understand things like, this is an LRU cache, and I want to do some sort of least recently used notion on the things, the soft refs I'm going to wipe out or not. He just has a pile of soft refs he has to wipe out sort of blindly and hope. Okay, so let's go sort through all the different things I've got here. Here's a summary of the services: GC, JIT'ing, Java memory model, thread management, some sort of fast time. JIT'ing includes hiding CPU details in the hardware memory model from people. Services that are provided below the JVM now, everything like threads and context switching from the OS, priorities, I/O, file systems, stuff like that. Then there's a set of services above the JVM, the application level stuff, thread pools and work lists, transactions or crypto models, or your user mode caches, JDBC driver caching, who knows what, models of concurrent programming, right? And then some of these new languages, alternative languages, might have different rules on dispatching or what it means to have an integer or concurrency. So I claim that I would like to see fast quality time move into the OS. Because with the TSC register, I get something very fast, assuming the hypervisor hasn't kicked in on me, but it's not quality enough. And I can call get time of day, but it turns out that that's not as fast as I might like or could get if I move the thing into the OS. All I need to do is have the OS tick a memory word 1,000 times a second in some user mode read-only page. And this would give me something that's coherent on a clock cycle basis. All the CPUs would cache it, and they're all one cache. It'd be cheap, it'd be coherent, whatever. It'd be easy to do. Thread priorities. The OS gives me thread priorities at the process level, but I want to have priorities where if I have a high priority JVM that's doing some sort of critical performance, latency performance thing like a web service, I want that to be able to starve out some other JVMs I might have, which are running some sort of batch-oriented background thing. You know, somebody's doing statistics gathering across a large DB, data mining. That guy needs to be lower priority than the guy that's trying to make money by having you click on a web page, right? But I can't specify that without doing it sort of at the entire process level. But then I get thread priorities within a process. And so I can't distinguish between GC threads, which need to have cycles ahead of the mutators, or else the concurrent GC won't actually be concurrent. It'll get starved out, right? And the mutator ends up blocking for a GC cycle. And the same story goes with JIT'ing threads. The JIT needs to get cycles eventually, or you will always run interpreted. And this was actually failure mode in the early Volano mark, where 1,000 runnable threads would compete at identical priorities to the JIT thread. And the JIT thread would starve, getting 1/1000th of a CPU, and the entire benchmark would run interpreted, unless the compiler with the JIT thread is given a higher priority than the runnables to go ahead and get his job done. Right now, Azul Systems is faking thread priorities with duty cycle style locks and blocks. We're getting the right set of thread priority games done, but we're faking what the OS should be doing for us, right? And we need it because we're trying to sell a low pause concurrent collector. We need the right kind of thread priorities games. But I claim this should just belong in the OS. OS is already doing thread priority games. It already does process priorities. It already does context switches. Why can you do thread priorities without requiring everyone to be root? Right? And then the other failure mode with everyone being root is if I take all the mutators and voluntarily lower their priority, then they don't compete well against, say, a MySqueal that's also running on the same box. They don't get cycles against the non-Java processes that aren't playing the same game, that aren't being polite. Okay, alternative concurrency models. These are things that people are looking for other ways to write large concurrent programs other than using locks. The JVM provides you thread management and locks, but some of these new concurrency ideas like actors and message passing, this is Scala and Erlang, or software transactional memory out of closure, or fork join, Doug Lee's fork join model. These are things for which the JVM itself is just sort of too big and too slow to move fast here. I think these experiments should be above the JVM, and they are now, and they should stay there until we get some consensus on the right way to do concurrency. And then maybe there's some interesting pieces that should go into the JVM at that point, like some sort of specific kind of STM behavior or some sort of magic fast park and unpark or cyclic barriers, or I don't know what it would be. But this is something where I want to see people keep doing stuff above a JVM. So fixed noms. Fixed noms are one of these funny things. I'll rail on it one more time and quit. They sort of belong in the JVM implementation, not in the high-level language implementation, because the JVM can do good things there. But the problem is that the obvious translation to infinite precision math at the Java level is fairly inefficient. We'd rather have some kind of tagged integer math. And the JIT can do magic things with tagged integer math to make it really cheap. But then I'll throw my 2 bits out and do a Bill Gates here and claim 64 bits ought to be enough for anybody. You the app-level programmer, know if you need more than 64 bits, and don't make everyone else pay for it. But I'm not a language designer, so I'll quit railing on the language designers. I gave this talk first to the JVM Lang Summit people, which are all Java language engineers or JVM power users, new language people. Things to keep in the JVM. So GC, JIT'ing, and the Java memory model all sort of co-intertwine in an intricate way. The JIT by itself really needs to be below the app unless you want to be in the business of doing x86 code generation. But it definitely belongs above the OS, and it's been above the OS for the past 50 years. So it works well there as a standalone separate process like GCC. So keep it in between that, and that puts it in the JVM. GC also requires debooks into the JIT'ing process. Because the JIT just really has to track pointers and know what they mean and where they go in order to do the right things with the right GC invariants. So that makes sense to keep that below the application as well. The Java memory model requires debooks in the JIT because it has to do with all kinds of games involving loads and stores and code selection, code scheduling. So again, makes sense below the app. These things kind of all are tied together in an intricate way, and I think that sort of defines what a JVM is. There's some of the alternative concurrency models being exposed by the new programming models people are looking at might enable faster, cheaper hardware with weaker memory models. But in order to do that, you're still going to need close JIT cooperation, which makes it still in the within the JVM. OS resource lifetime management. I claim that finalizers are not the right way to do that. Move this outside the JVM, make the application do some sort of lifetime management, whether it's reference counting or arenas or some sort of lifetime management. There's lots of different techniques here. But don't burden the GC with the knowledge that more of resource X can be had if only finalizers were run right now, right? And same thing for sort of weak, soft phantom refs. There are some interesting, very rare use cases for some of these, but most of them are, I don't think GC should be changing application level semantics. If I have a concurrent GC and it's running at a high cycle rate on you, and you make a soft or phantom ref, cycle by cycle, it could go to 0. You could make it one cycle, and the next cycle could be nulled out. And is that a useful programming model? And I do have programs that will crash when that happens, and it happens fairly easily, actually, with a good concurrent GC. So summary. Move some of these things that are in a JVM now into the OS, thread priorities, fast time access, resource management for the, should get moved out, fixed nums, tail calls, closures, moved in. Azul Systems is doing some different stuff, so this is now going to be Azul System specifics, my 2 slides of that. We do very aggressive virtual memory to physical memory mappings. More or less, we are in user mode controlling the virtual to physical mapping. And that requires terabyte a second remapping rates, which we can't get out of memmap and memamap and friends. So we need OS hacks to do that right. This is still going to be safe across processes. You don't break process safety. But if you screwed up within a process, then the JVM's got a bug and it crashes. And JVMs have bugs and they crash. That happens. So this is something we just have to fix. But if we do this, we get this really nice GC, which handles sort of memory of any size with the sort of low max pause. Hardware performance counters. Intel sort of screwed it up here in that they didn't make it cheap to get at the hardware performance counters. They have to go to a kernel, which you have to do a kernel context switch in and out. But the JVM's a natural consumer of hardware performance counters. I wish the hell it was cheaper to get at them. He can take perf counter data, remap it back to bytecodes, and from there into like Java lines of code or whatever. And that's all up to the JVM to do that mapping if I can only get that damn code out of the kernel in an efficient way. So Azul's doing thread priorities by hand. We'd like to see that go into OS fast time, but we'd like to see hardware perf counters come out into user land because I want to screw with them and look at them. And same with virtual physical memory mappings. So yeah, summary. There's work to do. And that is it. And I have a few minutes to take questions.
You mentioned a lot of code optimizations. Is there much going on in the area of data optimizations? Like the Java model has each object be its own garbage collectible thing.
Right. Okay, so there's a lot of code optimizations. Are there a lot of data optimizations floating around? Hotspot right now doesn't do a lot of data optimizations. It's sort of like value objects. There has been a push for a long time to bring up the notion of value objects, where, for instance, if you had an array of points, you didn't have to have a Java object header for every point for the billion points you wanted to draw your 3D rendering scene, right? I don't have a good answer for that. I have my stock bad answer, which turn an array of structs into a struct of arrays. It kind of gets rid of the overhead that way, but it makes it obviously less convenient to manipulate and use those things. Azul Systems went to a one-word object header a while ago. That was a little bit of data layout change, but that's sort of been it. We're looking at changing the layout of strings. Well, we've changed it once already, but we might change it again to be a more dense format. That's sort of it, though. No whole-scale interesting data layout optimizations going on. An escape analysis is not enabled. That's not a data layout game.
Well, they're getting rid of the object.
They're removing the whole object itself. They're trying to register the object, and it's not turned on because it has. I assume it has bug issues. So let me go this guy and then you. Yeah, go ahead.
You talk more like about your opinions on software transaction.
Oh God. Okay, can I talk more at length about software transaction memory? Yes, I can. Should I? Probably not in this context. I think it's the wrong way to do programming. I have a large set of slides. I have a full, 45-minute talk on why it doesn't work. That I'm not going to do right now because I have a hard deadline. And so let's just say that I think it's the wrong way to do. If you Google me and software transactional memory or look on my website, you'll eventually find, me blogging about the evils of STM. Now, not Josh, one behind.
Let me add one line, which is, but multicast is still good for power users.
Multicast is still useful for power users. I will agree to that. Why am I comfortable enabling users?
Yes. I mean, why not give them the worst possible timestamps and so exposes their bugs so you don't fix them?
Okay, so that has two different answers. One is I like enabling users because it's how I get my, my good feelings about myself in life. I'm helping other people fix what they claim is their problem. And then the other one is at Azul Systems, we fell over everyone else's broken concurrent programs because our memory model was much more out of order than an x86, and our programs that would run on an x86 but had data races that would not appear on an x86 or would appear rarely on an x86, those data races would appear frequently and quickly on an Azul box. So something that would crash once a week in production on an x86 would crash in 10 minutes on an Azul box. And at first, people claimed our hardware was broken, and eventually they figured out that no, in fact, their programs were broken, and they were happy after a while to go fix their programs and happy that we discovered their bugs because they'd have been eating their lunch in production for years on end. But it was a very painful path to go down, to go tell people that your program is busted, and I'm going to make it obviously by making my new product dysfunctional on your application. So I think that is not a good business model, although maybe it would be a wonderful, theoretical, I love the world model.
You said bytecodes for lousy format for program instructions. Could you elaborate?
At the time that Java bytecodes were out, there were other formats, lots of other formats being explored for how to pass around program semantics. In particular, right after Java became sort of semi-popular, Microsoft put out a bunch of research work on a different alternative format that was clearly superior in a number of ways. Since that time, people have done a lot of work on Java class files, sort of kind of backwards compatible. Bill Pugh's big on this, that makes format a lot denser, for instance. But still, the act of turning bytecodes into JITted code has a lot of hoops you have to run through. That with a little forethought and designing. If somebody who knew how to write a compiler had talked to the designer of the bytecodes, who's not here today, things would have been different and a lot easier. I can name you a bunch of tricks. Here's one. If you have a full register format instead of stack format for your bytecodes, you can pre-register allocate it so that it has a correct register allocation for a 7 CPU, and then I double that, a 16 CPU, a 14 CPU, and a 30 CPU, 30 register machine, a 8, 16, and 32 register machine. Subtract one for those, and then the JITting process could have been as cheap as take the bytecodes, unpack them, unfold the register allocation of flavor of choice, and you wouldn't have to do anything more than straight up stupid code generation to get it gets you an uber fast JIT for the first tier JIT. As it stands now, JITting that first tier of Java bytecodes is substantially slower than some of the alternatives that are out there for no real good reason.
A lot of the things we run have very high memory utilization, so there's a lot of data that you don't have, present in RAM. And so like between C++ and Java often comes down to C++, you can keep that data there, and you can have a lot of memory utilization and not worry about it slowing down the garbage collector. If you run with lower memory utilization, you can make it so Java can run as fast as C++.
It sounds like an ad for Azul Systems.
Yeah. So what can you do to make high memory utilization?
We changed GC algorithms to one that is independent of the size of your heap. So we have, people in production with 300 gigabyte heaps with, max pause times on the order of, 10 millis. And then we have our x86 stuff, for which we have seen people do, I think, 100 gigabytes with max pauses or, a handful of millis. We changed GC algorithms. We have a better GC story. That's sort of, half of the business model. So it is a solvable problem. Doesn't help you unless you buy our gear, but you can talk to Azul people.
Another question. So you said naturally but it seems to me that it's basically using the bus like a CPU. So why doesn't it come out of the
Because it's too big and complicated and it crashes. And if a JVM crashes but leaves your box up, that's a more pleasant situation than your box hardcore crashes and you have to go power cycle it. It's true, but how often does your operating system crash here? Right? And how often does your operating system go down versus a Java virtual machine go down?
And you want different flavors of JVM for different kinds of applications.
So if you're in the embedded handheld device, the OS and the JVM are sort of, might imagine them being basically one and the same. And then, yeah, then whether or not you're within the kernel or outside the kernel sort of moot. At Azul Systems, we did a microkernel OS, more or less microkernel style, but we kept it as a kernel to get process protection across JVMs in case the JVM crashed. And after a while, the kernel became very stable, and machines would essentially be up until they got power cycled. But the JVMs were undergoing rapid evolvement, and they had bugs, and they would crash. And it would be nice to not bring the whole box down. If you've got an 800 CPU box and it's got 20 JVMs running on it, if one of them's got a bug, you don't want to bring everyone else down.
So one of your slides in bullet points says deoptimization is hard. Can you elaborate on that?
Deoptimization is the act of taking an optimized running piece of Java code. So Java code plus all its inlines, code instruction selection, register allocation, inlining, loop unrolling, everything under the planet, and then discovering that deep in your inner loop, you had a virtual call that you made static and inlined and unrolled and replicated and yada, 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 and somebody loaded a subclass that now made that virtual call truly virtual, and you have to different code. Furthermore, right after they made that, after they loaded that class, they made a new object and stored it in a global and published it, which your other thread immediately picked up, and the next round through that entirely heavily optimized unrolled loop had better pick up the new virtual call when it picks up the new object. And to make that all work correctly is sort of, it's semi-hat trick there. I can discuss in more length, although I'll probably be out of time to do it justice. It's basically something I figured out while I was a grad student at Rice. I put in the first version of the server compiler hotspot umpteen million years ago, and the idea sort of spread around. But really, you need to track the Java virtual machine abstract state in the compiler and be able to rebuild it at some point during some point in that loop where you're going to acknowledge and recognize the loading of another class and get that all to work right. And then once you acknowledge it, you have to take your stack frame, which is this heavily optimized thing, and unpack it and rebuild it as, for instance, interpreter frames, which then might get later re-optimized. I don't know. But that whole job is very machine-specific because you're rebuilding actual frames on the stack. It's very JIT'ed code specific. It's very, it's a bunch of things. It's a lot of things are all tied up together in a tight little wad there. Well, I am going to call it quits because I have a hard deadline and I want to be out the door shortly. So thank you very much for your time and attention. And really